Let's talk a little more about representations and how that relates to Coulomb's law and electrostatics. So the situation here that we're going to work with is that we have two beads. One is plastic with a negative charge, and the other's glass with a positive charge. The glass bead is initially sitting on a surface, and the plastic bead is in air. Now we're not obviously going to worry about the forces acting on the plastic bead. We're going to think about the forces acting on the glass bead. Now all three of them are shown already. We have the gravitational force down, which is due to the mass or the weight of the glass. We have a normal force up, which is due to the bead pressing on the surface. And then we have F1 on 2, which in this case is going to be the Coulomb force, or the electrostatic force, which is the attractive force between these two beads. Now note that that little arrow is drawn here because the direction is specified. It's up because it's attractive. So if we wanted to draw this as a free body diagram, this is a really good start. But there's one other thing that I would want you to do. One of the things you might think about is a coordinate system, which is actually specified here on the side. But the second thing is to talk about the net force. Now, this is an example problem from the book, but even without knowing the entire situation, we can ask ourselves here what's going on. What is happening with the net force? Now, if I add up these two upward forces, it looks like that is actually going to add up to my downwards gravitational force. And so that would be F net equals 0. And you would want to actually label that because otherwise I might just think you're bad at drawing and maybe these weren't equal. So why would the net force be equal to 0 from an intuition point of view? Well, our glass ball is still sitting on the surface. How do we know it's sitting on the surface? There's a normal force. If it was leaping into the air, the upward force would be larger, but in the process of leaping up, we would actually have 0 normal force. So given that we still have some normal force, we actually say that it is resting on the surface, but the net force is equal to 0. It's not accelerating. It's not accelerating into the surface, and it's not leaping off. So effectively, if we didn't have this plastic bead here, the glass bead would be sitting on the surface with a normal force equal to the gravitational force. But with the plastic bead, we now have an additional upward force, which means our normal force is smaller. So if this was a scale, it would actually measure less weight. So what you could do is then calculate, for instance, maybe what does the charge need to be up here instead of it being specified for the normal force to go to 0. And that's actually the limiting case where the glass bead begins to accelerate upwards. And in that case then we would say the normal force goes to 0. F1 on 2 then would equal Fg. So please do think about drawing free body diagrams carefully. I encourage you to not always just draw them directly on the picture. It is more helpful to draw them off to the side so that you can clearly label things and prevent your picture from getting too busy. Okay, now I want to talk about superposition. Again, we want to think about representation, and this is again an example from the book, but I want to talk through it in a slightly more straightforward, simple way, so I'm not showing these three pieces, so I have them covered up for right now. And the question is, if we have these two charges here, Q1 and Q2, if we were to put a third charge somewhere, where could that charge go such that the net force on that charge is 0? And this is a lovely problem that comes up a lot in electrostatics, and the math can be a little bit tricky. One of the things that will make the math easier is if you do this graphically first and make a good choice by understanding the fundamental concepts before you jump into the math. If you have no idea what you're doing conceptually and jump into the math, you're never going to get this right. So let's consider 3 different regions where we might place this third charge. And in fact, it doesn't have to be along the line. This is a two-dimensional problem. And what we're going to keep in mind is that wherever we place our charge, we're going to have 2 forces acting on it, one from Q1, one from Q2. So we are not asking what force does Q1 and Q2 act on each other. We don't care about that. We're asking about the forces that each of these act on a third charge. So let's look at this region first. Let's place a charge here. So this charge is going to be labeled A. Now we've calling it charge 3, Q3, because we already had 1 and 2. So this arrow represents 2 on 3. This arrow represents 1 on 3. Now based on the directions, you should be able to determine, even though it's not shown, whether this charge is positive or negative. So pause the video and think about that. Do we know if this is positive or negative? Well, the answer is that it actually has to be positive because we see that it is repelling, right? So let me draw a little plus sign there, right? That Q2 is pushing Q3 away. So that's only going to happen if this is positive. If this was negative, we would have an attractive force towards each of these. So we know that this is positive. But what we were trying to do was to actually find a location where the forces add to 0. And here we're going to do that graphically. If I haven't told you exactly what the value of Q3, Q1, and Q2 are, well then we actually have to do this graphically. We can't just calculate these values out. So remember that you can add vectors graphically by doing the tip-to-tail method. I've traced out roughly what this vector looks like, though you can't quite see it, and I can move it over here. So then what my total force is going to look like is in fact from here up there, right? So this is F net. And this gets a little vector symbol because it has a magnitude and a direction. So it is roughly up. Does that 0? No, it's obviously not 0. It still has a magnitude. So this is not a good place to put this charge and have 0 force on it, 0 net force. In fact, this will experience a net force and accelerate away. So a second place we can try is this region. So here, again, it's going to be a positive charge, and so it's repelled by both of these. So why is F2 on 3 larger than F1 on 3? Well, because it's closer to this. So again, in the problem, maybe it's the case that Q1 and Q2 actually have the same magnitude of charge. I haven't specified that. But as long as they're somewhat similar and Q1 isn't much, much, much bigger, then in fact, the force from 2 on 3 is going to be bigger because they're closer. Distance matters a lot because it's 1 over r squared in the equation. So if we place our charge outside of these two positive charges, we can't get 0 net force because they're both repelling it. So again, this charge, B, is going to experience an acceleration to the right. So that leaves for us this region. There's going to be some position, some distance, where in fact we have a force to the left and a force to the right that are equal in magnitude. At that case, when you add them up, you get 0. So one thing to be careful of is that this position isn't necessarily in the middle. If these two charges were exactly equal in magnitude, then in fact the position would be in the middle. But if you look, this doesn't quite look like it is in the middle, and so it's slightly closer to Q1. That means that Q2 actually has a slightly larger charge. Now, one thing to be careful about is, again, labeling these very clearly. So this is our charge 3, right? This is 3. Oh, pen tool. This is 3. And so note that 1 on 3 is this one to the right. So that's pushing it away from 1. It's okay that it's pushing it towards 2. Charge 2 has nothing to do with the interaction between charge 3 and charge 1. Charge 2 pushes charge 3 to the left. So again, make sure that you're clearly labeling these forces. Subscripts are a great way to do it. The last thing to note is, again, the visual representation here was very important, and you need to define your coordinate system. You're not always going to be told what position to use for 0, but in this case, we've defined this charge to be at a position of 0, x equals 0. This charge is then at a position of x equals 10 centimeters. these sorts of situations, that's a really good choice for the coordinate system. If you pick a random position set to 0, your math is going to be much more complicated. So hopefully this reminds you a little bit about how vectors work and stresses the importance of showing everything through a clear visual representation.